Hello guys, so let's continue our journey of exploring graph like a pattern. So we covered almost everything under shortest path, and now we are moving to the next category. So there will be questions or problems where all the nodes which are given in a graph, we need to find a way or a minimum cost to connect all the nodes. So if you see, there are 1, 2, 3, 4, 5 nodes in this particular graph given here. What if you are asked that make sure that from any node you should be able to reach to any other node? That means you need to build a connectivity, but the cost of that connectivity should be minimum. And obviously there will be some ways given to you that what will be the cost of connecting, say A to B, if A and B are two different vertices and or nodes. So that is called minimum spanning tree, right? Ultimately, you need to build a tree, not a graph, because when they are saying minimum and cost should be minimum, that means there should not be a cycle. If you already connected, like say this A to, let's call this as a B, then you can anyway go from this C via A. So you need not to create another edge from say your 0th node to 10th node, because you can go via this. So that is why it will always be a tree. So let's explore this. First we will cover Kruskals, and our DSU union find basically will come under it. So okay, let's first explore the problem. What is the problem? How can we solve it? And then let's discuss the nitty-gritties of it in the next section. All right, let's check this question first. So this question is saying minimum cost to connect all the points, very similar to what we were discussing, right? Basically you need to connect all the nodes. So you are given points. We know how to calculate the distance between 2 points using Manhattan distance, simple mathematical formula. Return the minimum cost to make all the points connected. All points are connected if there is exactly one simple path between any 2 points. So now here, so this graph we have seen in our Google Sheet as well, Google Doc as well. So if these points are given, basically to calculate distance between 0 to 2, they gave us a formula. In another question, it can be like directly you are given an edge that if this road need to be built between 0 and 2 vertex, then the weight or cost you can say will be say 3 or whatever, right? So they'll give you the edge. Now our job is to build or choose edges ultimately, which we are going to build so that the overall connectivity cost is less. Let me draw this graph to build, what you can say. Let me draw this graph to build the intuition how we are going to solve MST problem. So imagine we are having this graph with some weight given, right? Normally what we used to do in our shortest path, what we were doing so far, from one source, say A in this case, you need to find out shortest distance to a target, maybe F, or to all the targets, or to every other node. And in case of all pair, we were saying that find shortest distance between every pair, shortest distance from A to B, shortest distance from A to C, from shortest distance from A to F, everything you need to calculate. Here problem is a little different, that you need to find the minimum cost, where we are saying that all are actually connected. There is just simple one way. Now imagine that this graph which is given above is just a cost estimated on some papers, that if we are going to build these roads, what will be the cost of that particular road. Now if ultimately I'm having these A, B, C, D, E, F cities, nothing is built. You have to choose as an engineer which road you are going to build so that all of them are connected, so that anybody from any city can go to hospital in another city, blah, blah, blah. But obviously the infra cost involved. So we are going to build the minimum infrastructure. What's the intuition here? First intuition is, yes, the solution of MSTs are greedy in nature. By greedy, we mean out of all the roads, which road is having the minimum cost? Build it first blindly. So obviously that one is minimum, right, between A to D. So we will go ahead and connect this edge here, and then we will add it to our ultimate cost. That ultimately cost is right now 1, plus we will see what will happen in future. Next is, what is the next? So if you see in our graph, this B to C is having 2. So B to C is not connected right now. So we can go ahead and safely build this, and my cost will now have 2 as well into the overall cost. Next, so 1 is done, this 2 is done. Next what we have is 3 clearly is basically the next cost. So I'll take 3, which is connecting D and C. So if you see, D and C are not connected right now. So yes, we should build this road. So we will go ahead and build this, and 3 is now also added in our cost. All right. After that, next is we are having this 4 here, right? And D and E are also not connected. So we will take 4 and we will connect this edge. 4 is now added in our overall cost. So next one we are having, let's suppose this is in place of 6. This is not 6, but what you can say, this is 5, right? So, but in fact, we have another option. So between A and B is the next edge which we are going to pick. C and F and A and B are almost equal. So even if it is lesser, so let's suppose A and B is the next one which we are getting. A and B is actually already connected. If we can see it here in the graph, that they do have a way to go from A to B. Maybe if we will build a road between A to B, then the cost to travel from A to B can be lesser. Right now the cost is higher because you are if there will be a toll or whatever on the road or in the distance, but we are talking about not the cost of traveling from one city to another. We are talking about building this infrastructure. So because A and B are already connected by previously built infra, we are not going to take this edge. So how we are going to do this in our algorithm, that we will see. But right now that is the intuition, that if something is connected, we will simply skip that road. Okay, what's next? Next, let's suppose this is also 5 between A to C. Then this A and C are also connected, we can see, right? If these two are also connected, then we are not going to take this edge as well. So we'll ignore this road as well. Okay, now next is C and F is the final edge which is left. Is C and F are connected? No, there's no way to reach to F so far. So we'll simply build this 5 and we will add it into our cost. Okay, so overall cost of building this infra is going to be the sum of all the edges which we took. Okay, so this is the intuition of Kruskal algorithm. Now if you come down to how we are going to write this algorithm, first thing, I think what is easy to see from what we discussed so far, we simply need to sort all the edges by weight. So that way we will have shortest, smallest one in front and then in the increasing order. If we have all our edges sorted, so our first problem is done. Then what we need to do is we just need to simply pick the edge and add the cost of, so pick from front and add the cost in my answer. Okay, so that's done. The only thing pending is we are also checking if the edge, whichever we picked, for example, A and B we picked here from my array, if vertices of A and B are somehow already connected. So we need to check if A and B are already connected or not. Okay, so for this problem, that whether they are already connected or not, this you can call it a sub problem right now. For that, what we can do is, the simplest way of doing it is, by simplest I mean optimized for time complexity. The best solution for that is to do a union find. Okay, assume you know union find right now. Even if you do not know, we will simply keep it as a tool for us, that in Kruskal we use union find to check this particular condition. Then we will use a standard code for union find. For now, we will not go into the depth of union find. That is a separate section. Take it as a tool that I'm having a you can say a simple piece of, very small piece of code which I can utilize. So I'll use union find, which should give me a method saying, so union find normally give you two methods, union and find. So this will give me a method called find vertex A, and I'll call find vertex B. If A and B, if answer of both find A and B is same, you can call it if find A and find B are same, then these are already connected. So this will be as simple as this. We'll see the definition of, we will see the implementation of this union find. So if from whatever we discussed so far, if I try to write an algorithm, how I'm going to write it. So I will have a method called, let's call it, okay, like how they're calling, cost of MST. That is my method. What they are going to send in this method is edges to us. Okay, and they are not going to, I think that is good enough for us to do everything. Then what is the first step we are going to do in this one? Sort edges. And by default, every sorting algorithm do it by in increasing order only. So no need to complicate this anymore. Sorting is done. Then what I'm going to do for edge, in edges, because this is already sorted, that means it will give me one by one sorted edge. So for edge in edges, that means I'm just iterating over all the edges. What I need to do, if, so edge contains what? U and V, two vertices. So if find U, assume find is a method available to me, equals to find V. So if those are equal, then I don't need to do anything. So I'll simply say continue. Let's just process the next edge. So this is if, so that it can continue. Otherwise, what I'm going to do inside it, I'll do in my answer, I will add the cost of the edge. So assuming edge has had two vertices U and V, and another thing called weight. Weight is nothing but the cost. So let's call it W for now. So in my answer, I will simply do answer plus equals to W. That will be the overall cost addition I'm doing. And I also need to update this union find that now U and V are connected. Otherwise we will lose this information, right? So let's call this is an extra line which I will do here. I will simply say union, assuming this method is available to me, U comma V. That's it. This will be my overall algorithm. In the end, return answer. Answer is nothing but the cost. Okay. So this is going to be on a very high level. This is going to be our Kruskal's algorithm. And this is Kruskal algorithm. Okay. Before we move forward and write the real code, production level code, think of the complexity of this. So if I'm having E number of edges, so this sorting is going to take E log E for sorting, right? That's the best thing you can do in sorting. So E log E is my complexity of this, plus there is a loop on my edges. So this is running E time. Okay. Now inside this, I'm actually hardly doing anything in this loop, right? So I'm doing a union and a find. So for union find, we will do the implementation, but worst case, it will be log of V. That is a given thing to us, that union find normally takes log V to find, and similarly log V to union as well. So overall, the time complexity is big O of E log V, because that is what I'm doing 2 times. So E log V is my overall complexity, time complexity of this algorithm. Once we have written the final code, we'll calculate the space complexity as well. Okay, let's just first write the code of that algorithm, which we just learned. And then we will move forward in the next section of this algorithm. So what we learned so far is question. So I'm using Geeks for Geeks because it is directly having the apply Kruskal's algorithm. This is the first question to learn the code actually. So they are having that you are having a graph where cost of building one edge is given, and you have to return the minimum cost to build the MST. So like we said, firstly, obviously we will have an answer. Let's call it cost this time, which is 0, and ultimately I need to return the cost. Okay. Now what we said is, if you can see, I'm already having union find methods. Intentionally, I'm hiding the implementation of it for now. We will discuss those, but let's not make it overwhelming, right? Let's go step by step. Assume you have union find right now. Then what we are going to do, so whatever we discussed. So edges are given to me, and it is not said that edges are sorted by any chance. Nope. Okay, so we will sort it. So edges, first thing is, should be a sorted list. So let's sorted edges. I'm doing it in Python, but it doesn't matter. Ultimately what we want is a sorted array. Edge on, what my edge is having actually is 1 2 3 things. So I want it to be sorted on W, which is 0 1 2 at the second index. So I'm assuming this will give me the sorted this thing. Then what we said is, for every U V W, which means nothing but for every edge in sorted edges, what I'm going to do, if my find, so find is inside this class. So let's just create the object of this class first. So let's call it disjoint union find. So DSU is equals to DSU. This is the way to create the object in Python, whichever language you are writing in. Ultimately you just need an object of this. And what is the size of my array? Should be the V, number of vertices, because I will insert every vertex into it, and this is based on 0, so it's fine. Now once this is done, I'll simply do if my DSU dot find, what I'll do is find my U equals to DSU dot find my V. If both are equal, then I'll simply say continue. Okay, otherwise what we were planning to do is cost, I will add current cost, because this edge we are going to include in our answer, And because we are including, that means those two need to be unite now in our final graph, so that we know that yes, they are same. So how we are going to do it? For that, like we said, we are having a union method. So same DSU dot union u comma v. This we are doing the union. Is anything else I'm missing here? Doesn't look like it. Let's just compile it to see. So basic normally works, which is working here as well. I'll submit it. Perfect. So this is what we discussed. So if you see, solution is like pretty straightforward. You just need to do sorting first, and then just check if these things are already connected in my answer. Then no need to build another road. If they are not connected, then just first build the road, which is union, and add the cost of that road into my answer, and that's it. It's done. Now I think let's discuss the union and find as well, because I wanted to skip this section, but life is not that easy. Okay, so we'll build this one. So I'll not go in deep implementation of union and find. I'll keep it very simple. Imagine that your target right now is just to write this union and find, which is hardly of 3 lines. This can also be like 3-4 lines only. It's just that this is the optimized solution here. That's why it is having more lines. But we'll just touch base this so that you do not stuck on writing union find if you are learning MSTs, right? And also you don't need to mug up the solution as well. So we'll come to a point where you know how to write union find. You don't need to mug up anything. So let's check that first. All right, let's try to understand union find. Let's try to build the intuition first, how this algorithm should be. So what exactly we are trying to achieve? So let's try to understand it in a simple way. Let's suppose we have 1, 2, 3, 4 different numbers or nodes. Now, if someone calls a method, say union 1, 2, then what it should do as a resultant is it should do 1 and 2 as one set, and 3 and 4 are still independent. After this, if someone calls 1, 3, then what it should do is, because 1 was already part of a set, so it should become 1, 2, 3 as one set, and 4 as separate. You can call it separate number or separate set. So overall, this is what union should do. I know it's pretty trivial, but this will build the intuition of the algorithm. Now, what find should do? So if someone calls find 2, then it should return the representative of this set, because 2 belongs to a set. Let's for now assume that 1 is the representative of the set. So find 2 will always give 1 as an answer. Now find 3 also should give 1 as an answer. And if I call find 1, then that should also be 1 as an answer, because 1 is the representative of this set. What is this representative? We'll come to that. In case of find 4, the answer should be 4. Let's call it find 4. It should give me 4 as an answer back. All right. Now, first thing first, of course, if I'll try to build it as a tree, you'll be able to understand it easily. But writing code, the code which we are going to write is going to be pretty simple. But writing code will run on array, And hence, first let's try to understand it on tree, what is going to be happening here, and then we'll try to translate the same understanding into array, and then we will see our code. Code will hardly be 3 line and 1 line like that. That's it. So first thing is union. So if I'm having say independent nodes, so obviously there will be so many nodes independently, same 1 2 3 4, right? 1 2 3 4. Okay. Now if same thing, if somebody is doing union 1 and 2, so it should be like 1 became the parent of 2. Okay. And if I am doing union 1 and 3, then 1 becomes parent of 3. Or another example, if you are doing union of 2 comma 3, then it will check who is the parent. So 1 is the parent right now, so 1 will become the parent of 3 as well. So and 4 is still a separate node. So if we are having like this, then now on this, when you run a find, so simply say find 3, so we will go up into the tree until we find a root node. In this case, 1 is the root node. Hence, whether you called find 3, find 2 or find 1, every time you will get same answer as 1. Okay, so this is the as simple as that. Now if because we are going to do this, okay, so from this understanding, let's try to write the code for it. How is the code? So assume that I know there is something called parent pointer here. Okay, that you know who is the parent of 3. So parent, you are having a knowledge in this vertex. So if that is the case, then how my find code should be? Find you, if you are saying, then what you should do? You should do that. And in case of root node, let's say how you will know that, you know, this is basically the root node. Root node will simply point to itself, means the parent of 1 will be 1 itself. So we'll say if my parent of particular, that vertex, if parent of u is equals to u itself. So in case of 1, so you will check parent of 1 will be 1 itself. Then no need to do anything. You can simply return. If that is not the case, so I'll say not you, then what should I do? Then what you should do is, then you will simply do, call this find again, find parent of u. And let's just see what we are saying here. Find parent of u, assign it to u, and ultimately what we are going to do is return u. This is a recursive code, obviously. So let's suppose someone calls with u equals to 3. Then what will happen? First, is parent of u equals to u? No, because parent of u is 1 and u is 3. Now what we will do is we'll call the same method, where in this method now we will pass u is equals to 1. Okay, so it will come here, is parent of u, which is 1, is same as u, which is 1 again. Answer is yes. So it will not go inside, it will return 1 from the recursive code. So we'll get 1 as an answer here. And now that 1 we got back from the recursion, so you will have 1 as an answer, and ultimately you will return 1 from the recursive code. So find is as straightforward as this. I'll come back to the complexity of this, but let's complete the code first. Now let's think of union. So if I'm having a method union u comma v, okay, and what we need to do in this case, let's suppose I need to union 3 with 4. So if 3 and 4 is my answer, so what I'm going to do, what I want in my resultant, I want that 4, either 3 becomes the parent of 4 or 1 becomes the parent of 4. Ultimately 1 will represent the 4, right? That is what we are saying. There is always one representative, right? So either 3 become parent of 4, then also answer will be the same, or 1 become the parent of 4, then also answer will be the same. So how can we do that? So if I simply say that first, let's call it parent of u, pu. Pu is what? Find u. So this will go recursively and give me the root of the tree, representative of that set, right? As we saw earlier. If we got that, then what we need to do? Simply we'll do parent of v, right? Because we are trying to union these two. Parent of v, who is the parent of v now? Parent of u. That's it. So if we are, so in this case, what we are doing is we are making that ultimate representative of the set as parent of the new node as well. So ultimately 1 becomes the parent of 4. So this is the code of union. So these 2 lines, and this can obviously be 1 line if you simply write it here, that parent of, if I replace these 2 lines with 1, parent of find u is equals to v, or the other way around. Parent of, like we did in above line, parent of v is equals to find u. Okay, because this will give the root node of u, and that root node of u I'm making the parent of v. This can be 1 line, but it doesn't matter whether it's 1 line or 2 line. Code is pretty straightforward. Now coming to the complexity of this. So there is obviously a best code of find and union, which gives us time complexity of log v, because that makes the tree always compressed. Means your one branch will never grow. But for MST purpose, I'm not going in depth of that. That we will cover when we will go in depth of union find. But for now, what is happening is I'm trying to find I'm trying to find root node of a set or a tree, you can say, right? So root node of a set, if I'm trying to figure out, that means worst case scenario, it is possible that all are in one set and sequentially made a parent of each other. Then the complexity will be order of n. But like we saw here, what we are doing is we are making representative as parent. So finding, if you see, is nothing but simply 1 line. It is always constant. Okay, because we are making the representative as parent always. So it will always be a flat only 2 level or 1 level tree. So 1 will always represent. So that will be the case for every set, right? So in case of find, it is almost constant. I'm calling it log v, but it is almost constant. In case of union, I'm doing find first, which we saw, it's almost constant. And then we are executing this 1 line. That is also almost constant. Okay. So union find is very efficient. That is why, to find out whether 2 nodes, why we are learning all of this. We are learning this to check in our MST. If I can go back. So in our MST, when we are simply trying to connect A and B, we were just checking whether this edge is required or not. So if they're already connected, that means if A and B are in one set already, then I will not do it. I will not make this edge between A and B. So union find for that is the best data structure. Okay, so this will give us almost constant time complexity. Having said that, the algorithm which we just saw is not the best for union find. Okay, but like I said, right now writing this code is good enough for us to move forward. and you will mostly be able to solve most of the famous questions available on internet using this simplest algorithm of union find. Okay, so we'll move ahead with this union find code. All right, so we just did a basic algorithm of Kruskal's. That means if we have to build a minimum spanning tree using this algorithm, we will be able to build. Before I move on to questions, let's just cover Prim's algorithm in the next video, and then I will take a separate section on advanced questions, I would say, on where you have to build minimum spanning tree, but that will not be a direct building a minimum spanning tree kind of a question, but more of like how you can think of building a minimum spanning tree to solve a given problem, right? We will try to go in that direction, but first let's cover the base, which is having our Kruskal's and Prim's algorithm to build an MST. Okay, so see you in the next video. Thank you.